Okay, so let me catch up to you guys. So as he's running, he's halfway. That's the point that I'm interested in. But I'm interested in this distance here. And it makes sense, as he's running to first base, that distance will get smaller and smaller. Does that make sense? Of course it will. I like it. So in general, what is this?
That's half the distance of the other side.
No, in general. So I've drawn it so that he's halfway, but I need to be able to represent him at any point between home and first base.
That'll be X.
X, I love it. Later, I'm going to put in place of X, I'm going to put half of 90. I'm going to put that in there, but I don't want to put that in there yet. It's too early. What's this? 90. And what's this?
The hypotenuse.
Yeah, I don't freaking know. So what do you want to call it? H? H. Q. Q? You can call it whatever you want to. You call it happy face?
Never get to the time of Q.
Let's do that. Maybe you reached out to me, you pulled my heartstrings. Q only gets all the charges, that's all Q, right? Yeah, but that's not much. Unless the charge is much. Charges like electric charge, not like credit card bill. Blah, 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 yeah. Alright, so we're going to focus, obviously, we're going to do several related rates problems, even though John saved your ass and actually asked a question. Maybe we'll do a few more. You try to draw the situation, if that makes sense. Can I set up an equation that relates the things that I know something about, the things that I want to know something about? So what equation is being screamed to be set up here?
Side.
Who?
Side.
Yeah.
Yeah, do I care about the angles? No. Alright, so if I cared about the angles, maybe I'll do some trig. I think that's what you're saying. Sine?
Q squared equals.
Yeah, so I just want to use Pythagorean theorem, right? So that would be
X squared plus squared. Q squared.
I like it. Cool. So I've got a relationship between the physical things that are happening here, and now I can do what?
Differentiate.
Take the derivative so I can relate the rates. Right? Again, I keep going back to the title of the section. Was everybody cool with this? Why did I put X there and not there? Because the way they worded it said, at what rate is his distance from second base? So I know that I want that to be my variable. I want that. Is that cool? That's how I knew to call that X. That's the distance from second base.
That's the distance.
No, that's the first base.
First base. I mean, just second base. Well, wait. Where's the part? When he's halfway to first base. Well, I guess at that point it doesn't really matter. But oh well. I want to use that there. It's just easier than trying to do from here. That's going to be a part of this triangle. Yeah, thank you. That was awesome. Total geek. What's baseball? So then how do I take this derivative? The really nice thing with that derivative is what piece of that is really nice?
If they're all squared.
90 squared is a constant. So what's the derivative going to be? It's going to be 2x dx dt. Good, because we're taking derivative with respect to time, because I'm talking about rates of speed, right? Rates of motion. That's 0 equals 2q dq dt. I like it. Cool. Now I want ice cream. I always want ice cream. So all right. So we actually did a lot of work here without doing a good first step, which is fine because we knew the formula. But what is that 24 feet per second? What is that?
Dx.
Yeah, dx dt. And what do you have to be careful about here?
Carry the units over?
Maybe, sort of, but it's negative. Right. Because my x is decreasing the way that I've defined it, right? So I'm getting closer to first base at that rate, at that speed. Cool. I like it. So now, I know this. I want to know what? What's the question?
QGDT.
Yeah, the question is how quickly is that distance to second base changing? And now looking at my related rates, I know dx dt. Do I know x? Yes, I do. Now I can plug in the snapshot. I want a snapshot at the time when he's halfway. So x is at a time when x is 45. And the 2's cancel. I might as well just kill the 2's. Is that cool? What about q?
We don't know.
We can figure out q, can't we?
Yes.
At the snapshot, when x is 45, what is q?
Staggering.
Good. This, right? So very often the equation you write that you take derivatives of is the equation that will help you figure out the values of the variables you don't know, right? Which makes sense. It's the relationship between those variables. It's going to be where you go to figure them out. So at a time when x is 45, can you figure out what q is? Hopefully you know it's not going to also be 45. Or will it be? So if I do 45 squared plus 90 squared equals q squared. I don't know what it is. Is that q or q squared?
Q
I'm
squared.
pretty sure that's q squared.
Q squared.
So it's q. Square root of that.
126,2305.
Blah, 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 blah. Okay, I like it. What did you get before that? Sorry? It was the square root of what now? What was that number inside?
10,145.
I like it. So to be honest, that's what I would plug in, because then I'm not rounding until the very end. Right? This is rounded. So if I go to solve this now, I've got everything I need. I just put that in place of q. And then I just got to divide by that. How's that? Is that? You guys see that? And you know, every step, what can I do? Draw the picture. Write the symbols for what they tell me and the symbols for what they ask me. An equation that relates those things. Derivative, and then I step back from the derivative and say, okay, what do I not know? What do I know? Is there something I need to figure out so I can plug it in? So in this case, we went, oh shit, we don't know q. So we figured q out. Sweet, now I can solve for dq dt and get something. I don't know. It's like 11 point something, or did somebody do it?
A negative. Yeah, you get negative 10.73.
It rounds to negative 11, that's close. So negative 10.73, blah, blah. What's the units? Yeah, feet per second, I like it. So if he's running towards first base at 24 feet per second, his distance to second base is decreasing by almost 11 feet per second. It's kind of nifty. Now, of course, the minute he turns his corner is a silly question. If he's running at 24 feet per second, he's going to be getting closer there by 24 feet per second. It's crazy. So what's interesting is, like, at this point, or some other arbitrary point, can you figure out? Of course you could. You just have to, if I was 1/3 of the way, that would be 30 feet. I would have put 30 in here for x, right? I would have to figure out what q was when x was 30. I could redo the whole thing. Well, what's your gut tell you is probably happening the minute he gets to second base? Now, this is kind of weird. What do you think? Well, this is very weird. I would love to just do that to see. I don't know if you guys see what I'm doing now. So I'm going beyond the question. I'm curious about what's the rate of change of the rate of change? I mean, does it start off big and get smaller? Does it start off small and get bigger?
It gets smaller and it gets bigger.
What's that?
The rate of change constant.
Yeah, is it constant? Well, let's do one more. Let's do this again. Now, because I'm in charge and I want to. So at a time when x is 30, when he's only 30 feet away from first base. So I guess when X is 60, the way I've got it defined. Is that cool? So if I do this again with X 60, it's the same setup, right? Just different numbers. So very quickly, if I want to know what Q was, it would be 60 squared plus 90 squared. Sorry? It'd be the square root of who?
11,700.
11,700? Alright, cool. I like it. We've already got the related rates set up, so now I just got to plug X would be 60, plugging it in here. 60, he's still running at the same speed, we'll assume. Q now is this business, dq dt, so if I divide by that, no, if you think about it,
Negative 13.31280471.
negative 13 something. Alright. So how does that relate to what we got? If he's a little closer, it's actually changing less. And I really want this to make sense. So I'm going beyond the problem. Are you guys cool with that? That's going to happen. It's already happened. It's happening at the moment. If I extend this, let's pretend like this is me, and I don't know about second base. I'm like, all right, run? Okay. If I kept running at the same straight line, at the same exact angle that I am, what's the closest I get to second base?
Getting on first.
And when I get on first base, right?
Yes.
So it makes sense then that this length of this thing is gonna, the rate of change of this length, it's gotta reach a certain thing, and then it's got to start to grow again. So it's the rate of change has to not be constant along that line. If you extend that out, it kind of makes a little bit of sense. Now that's beyond the problem. That's nothing that they ask you in the problem. Are you guys with me? The whole thing we just did, that's the first part of the problem. Was there more than one part? Yeah. The second part is just about distance from third base. So do the whole thing again, but you draw out to third base. And then your triangle now. What do you think is going to happen about third base? You got the triangle on this side now, right? You guys kind of with me a little bit? So it's going to be the same thing.
A positive, yeah.
Yeah, exactly. I like it. Yeah. All right, maybe. So that's all the problem wanted you to do. What I just did was beyond it, but I like doing that. Okay. Anything else specifically from?
Exactly the same.
Say again?
Is it going to be exactly the same thing?
Just like you said, it's going to be, at that point, it's going to be the positive. Because at this point, it's a mirror image, right? Now at this point, the rate of change of this distance would be the same as it would be at that point from here. Because again, the mirror image, right? Maybe. It feels a little bit like cosine and sine, and how one's growing and one's shrinking, and blah, blah, blah. That's enough of that. Sorry. Okay. Anything else I can make weirder than it was originally? Alright, so what I want to do right now is just take a look at some of these right out of the book. So if you don't have any specific problems,
I said to go to 26.
here we go. $26.
Yeah.
Oh yeah. All right. All right. I didn't sign this one, did I?
No.
No. Okay. Good. I think I signed it in previous years. What's going on with this problem? I mean, is the rate of increase or decrease, in this case, what is it doing, being filled? Is the rate of increase going to be constant as the water goes up?
No,
Why?
because the width of it is actually increasing as you go.
Yeah,
higher.
so right here there's an abrupt change, right? And all along here there's it's different. The width is different, like you're saying. But then there's an abrupt change right here. So the minute I get here, it's like it's going to be a disconnected graph. It's going to be an instant weird change. I guess kind of again, I'm going a little beyond the problem, but that's the shape they've given me, and that's what's going on with that shape. So the question is, at what? The pool is being filled at a rate of that. How fast is the water level rising when the depth at the deepest point is 5 feet? And let's see, what do they give me? Oh, this isn't as bad as I thought. This is 6 feet here, right? Oh, so this doesn't even come to play then. So if the depth is 5 feet, so I'm still inside here. You guys know what I mean? I thought it was going to be even neater and say, like, when you get out to here, that's where things get a little bit weirder, right? If you're at home, we'll talk about that problem. Okay. So go ahead, take a couple minutes here and see how far you can get. Try to just summarize what they've told us. The real problem on this one is the formula that you're going to use.
Are you using multiple formulas?
Not totally. No, not really. Just to help you out a little bit. The cross section, and I'm at 5 feet, so I don't have to worry about any of these other little things up here, right? I'm at 5 feet, so I'm in here. What shape is that cross section in? Trapezoid. There's no trouble.
Not quite.
Huh?
Yeah,
Totally.
Yeah,
Isn't one side like mostly?
I don't care. Trapezoid is defined to be a shape where two sides are parallel. The other two sides can do whatever the hell they want. If the other sides are also parallel, then you got a parallelogram, right? You got a specific kind of quadrilaterals, a specific kind of trapezoid. So trapezoid officially has only two sides that are parallel. The other two have to be at odds with each other somehow. So I know the classic shape, even the classic shape of the trapezoid tells you that, right? Pretend like that's a trapezoid. Yeah. So these are parallel, this side and that side, and these are not, right? And that's really what that is, just turned over with one side a little more extreme, right? Sure. All right. I like it. So, let me see. Try to draw it the same way. Alright, so it doesn't really matter what happens up there because I'm at a point, oh my gosh, it's really choppy water. Alright. So how high is this in general? H, that's right. This, now here's where things get interesting. This, how wide is this? This is always going to be 12. Is that cool? So really the question is, how wide is this? That's the question. And also there's something, do you guys understand? We've drawn a cross section, so I'm talking about the area of the trapezoid, but what's the real problem I'm talking about? I'm filling a pool. Thankfully it has more than 2 dimensions. Yeah, the fact that it's, where'd it go? 20 feet wide, 40 feet long. So what the cross section I'm looking at looks to be 40 feet.
That's the 40.
So this way is how much?
20.
Yeah, 20 feet wide, 40 feet long. Now stay with me now. So how do you get the area out of this? If I know the volume, if I know the area of one face of it, and it continues all the way along its length, how do I get the volume of that? So what I really have, just let me see if I can do this. It's not bad for me. I'm going to stop there. I always have trouble with representing that thing, but screw it. I don't know, how do you do that? Where are my artists?
Just go down. No, you go down straight.
Oh, so close. I'm excited for you.
Screw it, all right then. So, if I take the if I take the area of this, and this shape is actually known as a prism. Right? If you're curious about what you call a trapezoidal solid, but a prism just captures a repeated shape. So you can have Toblerone. You ever seen Toblerone? You ever eaten Toblerone? Anybody have any idea what I'm talking about Toblerone? Right. So it has this shape basically. That is a prism because it's a repeated triangle. Cookie dough that you can buy in the store is a cylinder, which is a repeated circular shape. Right? Before you eat it. Your equation can have all your T parts in there. So the way to get a prism's volume always is the area of the base times the height. And the height in this case would be the length, right? And that works for every time. The volume of a cylinder was the circle times the height. The area of the base times the height. Why is it a big ass B? Because it's not just a line, it's an area of a base. So that's why that's big ass B. Right. Okay, alright, so in this case, our volume formula is going to be the area of that trapezoid times, I forgot already, what was it, 20, right? That's 20, that would be 20. This is 20 feet. Okay. So what is what is it that I don't know that I need to know? They told me that this much is 6. Well, that's not really helpful. I need to know what this is. Right? Because the area, I don't know if you guys remember the area of a trapezoid. What's the formula for the area of a trapezoid?
A small, lower side plus upper side divided by 2 multiplied by the height.
Beautiful. So what's the area of a triangle? Half the height of the base, right? You with me? No, you're right. I just want to catch everybody else up with what he said.
Yeah.
So it's half the height times the base, but how many bases are there? 2. So it'll be base 1 plus base 2. That's the way I remember that formula. It's not really why it works the way it does. It's a way to remember it. 1/2 the height times the sum of the bases. I like it. So I don't know how wide this base is at some arbitrary height. Right? Or do I? Is there a way to figure that out? How wide is it if it's here? How wide is it if it's right here?
It's
Yeah, 34. Because the whole thing's 40, so that would be 34, right? So that's doesn't this feel like our cone problem? Let's see if we can't make that the same. So before it goes to the weirdness up here, this totally would be 34. So at some arbitrary height, how wide is this? That's really the question I have to figure out, because I got to know what the other base is.
Is it the middle line? No?
It's a 6 minus h, I guess. Because it's 6 feet to the where the 34 line is at. So if you use 6 minus h, maybe you could.
No. So this is for any height of the water. So I could have the water here. Does this help if I just put the water there? There we go. So that's h.
Isn't middle line also trapezoid? Middle line. That it's like base 1 plus base 2 over 2.
So and that would be what?
Middle line over here. So it's 12 plus 34 and divided by 2.
Would give you the distance across at the. So this is going to be at any position,
Yeah.
not specifically in the middle, right?
Yeah.
This is going to be at any height. So yes.
Wouldn't it be 12 plus V2 if V2 were the top one over 2?
So let's break this down. All right.
Since the bottom would always stay the same. Well,
Yeah, the bottom's always 12. I'm with you on that. So isn't this, like, just draw on the water right there. I think it's going to help out a little bit. So how much wider is this than 12? I add this little bit in here, right? That little triangle there. And I add this little triangle in there, right? That's how wide it's going to be. So it's going to be 12 plus whatever this width is here. Let me let you absorb that for a second. Why do I need to know this? Because that's going to be like base 2. It's going to be in my formula, right? Base 1 is 12. Always. Base 2 is, oh shit, it depends on the height. So then I feel like the cone and the radius, depending on the height, the further you go down, the less the radius was.
Yeah.
So we found an example, a relationship between those. So how can I find a relationship between these? Well, the beautiful thing is, there are similar triangles, but there's also similar shapes in general. Then they just have to be triangles. I don't know if you guys know this. Alright, so I need to figure out how wide that is and how wide that is, or I need to figure out.
16 and 34 minus 12 and 6.
Don't you just do like the height is to base 2 as 6 is to 34? Like,
There you go. Okay, cool. So you could either try to do this, try to figure out how wide that is, and that I wouldn't think would be very easy, or you could use.
What he said,
Yeah.
It's 6 feet tall,
Take some of this away.
so that's 34 feet wide.
Yeah, so the whole height here is 6, yeah, for that little piece that we're talking about. Cool, I like it. So when it's 6 foot tall, it's 34 foot wide. So when it's h foot tall, it's b2 feet wide, right? So I'm trying to figure out a relationship between these two, because right now, what do I have for an area formula? I have half the height times 12 plus b2. Too many variables in there. And the volume, let me just go ahead. The volume would be the width times the area, so that would be times, what was it? 20. I like it. Cool.
So we are going to look at triangles,
Yes, exactly. And we're going to look at, well, sort of.
sort of. I mean, you said that we would have to find some parts of it.
You
right?
could. That's one way you could try to attack this, is to figure out what that little piece is there and what that little piece is there. Right?
Yeah.
Not the easiest thing in the world to do, possibly. But instead, what can I do?
34.
When it's 6 foot tall, it's 34 feet wide.
Equals B2
H
over
over B2.
6 to the 8.
H over B2.
Now, when it's 0 feet tall, how wide is it?
12.
12 feet, right? So, if you wanted to do it, I'm trying
H
to
to
remember.
12.
Let me think. See, there's got to be an easier way than that. Well, the problem is it's not like a full triangle. I mean, do you guys see the problem we run into? At 0, it's supposed to be 12, and that's going to throw the multiple off. So you can't use that for a trapezoid unless you have the complete triangle, right?
Does that mean you have to basically make 2 equations and then set them, I guess, equal to each other, and then solve for one variable? So, like, you have 6 over 34. You know that that's, you can fill that in for the area of a big trapezoid, and then set that, and then compare that to the small one, the H and B2 trapezoid. I mean, and then and then after that, solve for one variable. And
I like the little triangles.
Yeah, maybe we do have to do it this way.
yeah, that's
The 16 and the 6.
like solutions, you know.
Yeah, and then we got, there. That's better, because then we know this was what? How much?
16.
16.
And it's still 6.
And so now the problem we get there is, let's see. So then I know B2. So this is what I was trying to avoid, but maybe this is the best way to do it. I've got this little bit here, right? So I can call it X, but then this little bit here, I guess we'll call it Y. Is that cool? So then B2 would equal 12 plus X plus Y. So now I got to take a minute to figure out what X and Y are based on H. So for example, X, 6 is to 16 as H is to X. Is that cool? All right. So that's why I was trying to figure out if there's a quicker shortcut than doing this. Because you do have to introduce more than one variable, but you're immediately going to write them both in terms of H anyway, so it'll work out in the end. There's got to be an easier way, but I just can't think of it. What did I just say? 6 out of 16. 6 to 16 is H over X. So then X is 16 over 6h, so 8/3 h. Let me stop there for a second. So whatever the height is, that little extra bit that B2 has is going to be 8/3 that height. I like it. And then for y, I could do the same thing. So how much was this again?
6.
So that's 6. And then this is still 6. I like that. So 6 is the 6 as, where'd it go? You can do it, Jeff. 6 is the 6 as h, there it is, h is to y. So that would be 1 equals h to y, so y equals h. That kicks ass. So now I know B2 is 12 plus 8/3 h plus h. No, I really want you guys. So I had to let go of trying to figure out an easier way to do it. So hopefully, I want to see if you guys understand what just happened and what was my motivation for doing what I just did. The formula requires me to have an expression for B2 because I have too many variables in here right now, right? So here's what the volume formula looks like with everything I knew right then. It's 1/2 the height times the sum of these bases. I don't know what that base is. So I need to figure out an expression for this base for any height that I'm at. So the thing that came to me immediately was just trying to fill this in. Right? Because that's how much bigger is B2 than 12. Well, it's this much bigger and this much bigger. I like it. Which explains why they gave us those measurements, but I'm still like, just kind of crook away. But oh well. So I wrote that. I said B2 is